My interest in physics actually started very, very early. Used to go out onto the front with the guy next door who happened to be a physicist and look at the night sky and try and understand where it all came from. And the nice thing about physics is it allows you to explain an enormous number of things with some rather simple concepts. So it's kind of natural that I did it at school and went on to university. And then in my final year, I got to learn about particle physics and in particular the neutral kaon system. And that's just such a wonderful kind of quantum mechanical playground where you can just have hours of endless fun. And so of course I wanted to do it as research, and I was very lucky to be able to get a research studentship which allowed me to go to CERN. I started working there. We produced some interesting results. We wanted to improve them, so I did a second experiment and then a third experiment. And then I started to change fields a little bit because I started off as a bubble chamber physicist. And bubble chambers had reached the end of their useful life, so I retrained myself as a counter-physicist and started doing electronics experiments. And then in the early 80s got back into neutral kaons, but doing what I really wanted, which is to look at the matter-antimatter asymmetries that are in the neutral kaon system. And from there we did a second experiment, of course. And then I started to move more into the higher reaches of science management. So I became deputy division head at CERN of the main experimental division, and then director of particle physics at the Rutherford Lab, which is the largest particle physics group in the UK, and started to develop new interests, still in particle physics, but to try and do something to recreate the spirit of the early pioneers in accelerator physics in the UK. The UK used to be a world leader in accelerator physics, and somehow we've lost that edge. And so I started to make the case for accelerator R&D as a subject in its own right in universities. And when I finished at the Rutherford Lab, I was appointed director of the John Adams Institute for Accelerator Science here in Oxford and in Royal Holloway, with the mission to train a new generation of accelerator scientists. What got me into this takes me back to the kaon system. The scientific interest there is that the neutral kaon is a beautiful balance between matter and antimatter. And there's a beautiful and staggering imbalance between the amount of matter and antimatter that's in the universe today. And in the late 90s, we began to realize that you could also create matter-antimatter asymmetries using something called neutrinos. And these neutrinos, we need huge, huge numbers of them. And one way of producing huge, huge numbers of neutrinos is to build very special, very powerful accelerators. And so we have now a strong program of R&D in the UK and also here in Oxford, trying to work out how to build something which could study matter-antimatter asymmetries with neutrons and maybe explain the matter-antimatter asymmetry in the universe, which takes us back to where I was when I was 12, 13, 14, looking at the night sky and wondering where it all came from. The institute here in Oxford was created in 2004 with the help of a grant from the Particle Physics and Astronomy Research Council. It's a joint venture between the University of Oxford and Royal Holloway, University of London. It's one of two new accelerator science centres. The other is the Cockcroft Institute based at the Daresbury campus, which is a collaboration between the universities of Liverpool, Lancaster and Manchester. And we're working collectively on two major projects. One is a linear collider, which takes electrons and positrons, accelerates them to very high energies and collides them together in order to study the structure of matter, to try and understand and uncover the next layer in what is sometimes called the cosmic onion. And the And the other project is neutrino factories and high energy, high power proton machines. In Oxford we have, and Royal Holloway, we have about 16 academic staff, about the same number of research staff, a similar number of graduate students, and comparable technical staff support. So it's about 50 people in total. As well as the main research lines, we've just started another research line which is related partly to the neutrino factory, but it's to design and build a new type of accelerator which we think could have applications in medical science. In particular, could be a very suitable accelerator for carbon ions, which can be used to treat certain cancers which are otherwise rather difficult to treat. Cancer treatment using protons is quite well established, although not so much in the UK. But over the last several years, the idea that treating cancers with heavier ions has in some cases significant benefits. But the traditional way of accelerating protons for cancer therapy is to use something called a cyclotron. And the cyclotrons are not really suitable for these heavier carbon ions. The traditional way of then going to the next stage is to use something called a synchrotron, which is exactly the same sort of machine as, for example, the Large Hadron Collider at CERN, or the new diamond synchrotron at the Rutherford Lab. These are excellent and flexible machines, but they are rather slower at the acceleration phase, and so therefore you're limited to pulsing them at 10 or 50 hertz. And I believe that there are occasions when you would quite like to be able to accelerate particles and pulse them much more rapidly, maybe at 100 hertz or a kilohertz. And this new type of accelerator would give that capability. So that's a very exciting project. And then the other two parts of our mission are, one, to publicize accelerator science and its benefits, not only for fundamental science, but for science in general and society in general. And then the other part of the mission is to train a new generation of accelerator scientists so that they can go out and work not only in the big particle physics labs like CERN and DAISY and Fermilab and the Rutherford Lab and Daresbury, but also to work in, for example, medical science or in industry, where, I mean, not many people seem to know that more than half of the world's accelerators of more than a few million electron volts are in hospitals. And that's the big market. And so I think, for me, it's quite an exciting option that you can take a new generation. And you know, some of the graduate students are both very bright and extremely motivated by this work. And in 3, 4, 5 years' time, we'll be turning them out, and they'll be finding jobs in all sorts of places which they and we never thought of.